welcome students to our third lecture on operational amplifiers. I am Dr. Kirti Vyas from Arya College of Engineering IT. Let's get started with the topic. As we already discussed, the symbolic diagram of op-amp, which is shown in particular slide with inverting and non-inverting input VCC and minus VEE connected to the terminal 7th and 4th and 6th is output. Today we are going to discuss about some of the parameters of op-amp. First of all, we already discussed in earlier class about the input offset voltage. It is the voltage that must be applied between the two input terminal of the op-amp to null or zero the output. The figure 2 shows that two DC voltage are applied to the input terminal to make the output 0. For a 741 op-amp, the maximum value of this input offset voltage is 6 millivolt. This means that a voltage of plus minus 6 millivolt is required to one of the input to reduce the output offset to 0. This is required in order to match the two transistors. The second parameter is about the input offset current. Like an input offset voltage, we also have an input offset voltage which is defined as the difference between the currents between inverting and non-inverting terminal of a balanced amplifier. The input offset voltage is denoted as IO, where IO subscript. In subscript we have IO, where IO denotes the input offset, which is equals to IB1, that is input current at the base 1 minus input current at the base 2, IB2. For 741, 200 nanoampere is the maximum value for input offset current. As the matching between the two input is improved, this difference between input offset current will become smaller. For a precision op-amp, the input offset current is about 6 nanoampere. Third parameter is input bias current. The input bias current denoted by I subscript B is average of the current entering the input terminal of a balanced amplifier. So the average means that it is IB1 plus IB2 upon 2. The value of the input bias current is about 700 nanoampere for a precision op-amp, and the value of IB is equals to, this was the maximum value, and the value of for precision 741 IB is equals to plus minus 7 nanoampere. The next parameter 4 is about differential input resistance denoted by Ri. The Ri is the equivalent resistance that can be measured at either the inverting or non-inverting input terminal with other terminal grounded. For a 741C, the input resistance is relatively high, about 2 mega ohm. For some op-amp, it may be up to 1000 giga ohm. It is quite large, as you can see. The input capacitance is the next parameter, Ci. Ci is the equivalent capacitance that can be measured at either the inverting and non-inverting terminal with other terminal connected to ground. The typical value of Ci is about 1.4 picofarad for 741C. Next is input voltage range. The input voltage range is range of a common mode input signal for which the differential amplifier remains linear. This is quite important to understand this particular parameter in order to make the op-amp work according to your requirement. It is used to determine the degree of matching between the inverting and non-inverting input terminal. For 741C, the range of input common mode voltage is plus minus 13 volt maximum. Next is very important parameter, common mode rejection ratio, also known as CMRR. The CMRR is defined as the ratio of differential voltage gain AD to the common mode voltage gain ACM. So we can write the CMRR as differential gain represented by AD upon the common mode voltage gain ACM, AD upon ACM. For 741C, CMRR is 90 dB typically. The higher the value of CMRR, the better is the matching between two input terminals and smaller is the output common mode voltage. So, if you want to understand that whether your op-amp will work correctly or not, you can go for the checking of these particular parameters. The CMRR value, if it is quite high enough, that is, the two transistors used for configure the op-amp are quite matched, and hence it will work quite correctly. Next, eighth parameter is large signal voltage gain. Now understand this. Since the op-amp amplify difference voltage between the two input terminals, the voltage gain of the amplifier will be defined as output voltage upon differential input voltage, also denoted as VO upon VID, VID for input difference voltage. Because the output signal voltage is much larger than the input signal, the voltage gain is commonly called large signal voltage gain. For 741C, the value of the voltage gain is such a high value. So you can see what the capability an op-amp has. Now the output voltage swing. The AC output compliance PP is the maximum unclipped peak-to-peak voltage that a op-amp can produce. Since the quiescent voltage is ideally zero, the AC output voltage can swing positive or negative. This also indicates the value of the positive and negative saturation voltage of the op-amp. The output voltage never exceeds these limits for a given supply voltage, that is plus VCC and minus VEE. For a 741C, the output voltage swing can be plus minus 13 volt according to the value of supply voltages. The next parameter is about output resistance RO. RO is the equivalent resistance that can be measured between the output terminals of the op-amp and the ground. It is 75 ohm for 741C op-amp. Next, we have learned about 10 parameters of op-amp. Now, we need to have insight into a numerical problem. Given example 1, you are shown a op-amp, and what we have to find? We have to determine the output voltage in each of the following cases for the open loop differential amplifier when input is VIN, this should be VIN equals to 5 millivolt DC, VIN2 equals to 0.7 microvolt DC, and this VIN1 equals to 10 millivolt RMS, VIN2 equals to 20 millivolt RMS, and the specification of the op-amp are given below. The value A stands for the value of gain, RI the input resistance 2 mega ohm, RO 75 ohm, VCC plus 15 volt, VE 15, and output voltage swing of plus minus 14 volt. Now the output voltage of op-amp is given by V output is equals to differential gain up into V in how much input has been, difference between how much input has been applied, VIN1 minus VIN2. So for this particular, we find out VO, which is equals to 2.4 volt DC, and The next, for the B part, the output voltage equation is valid for both AC and DC input signal. So the output voltage is given by almost substituting the value, we find out equals to minus 2000 volt RMS. The theoretical value of the output voltage we have found out, and the op-amp saturate at plus minus 14 volt. Therefore, the actual output waveform will be clipped as shown in the figure 5. See the figure 5. The V in 1 has been shown, V in 2 has been shown, and V output, you can say it is a clipped. Instead of the sinusoidal, at the top you are having a clipping at the 14 volt peak, and at the negative end also we are having a clipping at 14 volt peak. So this is how we have found that given the input voltage Vin and Vin2, how the output of the op-amp will be there. It will be according to the last clipped waveform, and it is taking a shape of a almost rectangular waveform. Next is output short circuit current. Now understand that in some application, an op-amp may derive a load resistance that is approximately 0. Even its output impedance is 75 ohm, but cannot supply large current. Since op-amp is a low power device, and so its output current is limited, the 74C can supply a maximum short circuit output current of only 25 milliampere. So the op-amp, according to this particular 25 milliampere limit, you can see the op-amp cannot be used as a current amplifier as such. It cannot be used as a power amplifier, but it is basically used as a voltage amplifier. Supply 12th is supply current. Is is the current drawn by op-amp from the supply. For 741C op-amp, the supply current is almost 2.8 milliampere. Next, the power consumption, which is denoted by PC, is amount of quiescent power that must be consumed by op-amp in order to operate properly. The amount of power consumed by 741C is about 85 milliwatt. Thank you for this particular lecture. In next lecture, we will talk more of the op-amp and its practical uses.